Welcome on Mathematics. Today you'll hear cars passing and birds singing because it's very hot and I don't really want to close the windows. Today we'll speak about axioms, definitions, theorems and logic. These four are the bricks you use to build all the mathematics. Likely they never told you were using them or never pointed out where you were using them, but trust me, we'll see we use it all the time and it's the right way to do things, even if it's terrible. Well, first of all, we'll speak about axioms. Axioms are a philosophical concept before being a mathematical concept. In fact, they were first used by Greek philosophers. They said an axiom is an indisputable truth accepted by everybody, which needs no proof because it's obvious. There's just one thing I have to underline, that is that the concept today is a bit changed in mathematics. For us, an axiom is just a truth that doesn't need a proof. This means we don't need anymore the concept to be obvious and accepted by everybody. It's just a rule we put there and we have to accept it and follow it. We will see in the future why this happens. Just to mention, another branch of maths complicated further the axioms, but we won't study that. Now, thanks to my friend the Cesium Man, I'll present a concrete example of what an axiom could look like. Oh, that's cute! Concreteness, examples, so we can understand things, it's so real. Don't get used to it, it won't last long anyway. Well, something we could all agree is that all the things on Earth fall downwards. Keep in mind the axiom we invented right now because it will be useful later. So, why are axioms so important? Because they are square one to demonstrate facts. And why this applies to them? Because they are, as we saw, truths that need no proof. So the idea is taking for fundamental things that appear obvious to us, which are the axioms, and then prove all the rest as a consequence of these obvious things. Think about it, without axioms we'd have an infinite loop of facts consequent to other facts. Instead, what we need is a primordial fact that gives birth to all the other facts. Can you remember the axiom we created earlier? We can use it to prove that if things don't fall downwards, we are not on the Earth. This is a very trivial example of a theorem. That's because a theorem is a proposition which is logically proven starting from axioms or other theorems. A theorem is made by an hypothesis, a thesis, and the logical proof that leads from the hypothesis to the thesis. Hypothesis draw what's your starting situation, while the thesis is the logical consequence of that situation. If the hypothesis actualizes, also the thesis will. The proof is a series of logical steps that leads from the ingredients, which are axioms and other proven facts, to the thesis. Obviously, there's no need to use all the ingredients at the beginning, you can use it in different points of the proof. Now we have clarified what the general structure of a theorem is. So let's get back to our example and talk about a hypothesis. Hypotheses are statements we use to outline a situation we want to discuss. What we do is to describe an imaginary scene, and doing so we define its borders. In our example, hypothesis could be the following. Imagine we are observing an object. Imagine we are in a room and we can distinguish the roof from the floor, so where's the above and where's the below. Imagine that the observed object is falling towards the roof. The thesis would be something like this. We are not on the Earth. Just to cover it all, the proof is the following. By hypothesis, we have an object falling towards the roof. By axiom, things can only fall towards the floor on Earth. By logic, being the below the opposite of the above, we are not on Earth. So the thesis is proven. Here it comes the evergreen question. Why do we need theorems? Usually theorems show bonds between things that seem to have nothing in common. That's not always true. From time to time we need to demonstrate obvious theorems. But I want to provide an example of the first kind of theorems, and it will be about something you surely used but you never noticed it was a theorem. The theorem I'm thinking about says something like this. If the sum of the digits of a number is a multiple of 3, the number itself is a multiple of 3. As you can see, I wrote a very big number on the screen. I first divided it by 3 in a classic way to find out, in case, the result. Then, instead, I use the theorem. It takes, with the classic procedure, 2 minutes and 15 to find out that the number is not a multiple of 3. That's because the division gives us the rest of 1. 2 minutes and 15, it's a pretty long time. You also risk to make mistakes, because there is a lot of calculation in it. Using the theorem, it just takes 45 seconds to find 67, which is not a multiple of 3. That way, we can just do trivial sums between the digits, find out the number, and avoid a lot of further useless calculation.
Matthew, we have calculators. Why would I need to prove such a tomfoolery?
True, we have calculators. Or better, we have computers. But, you know, also computers take time to calculate, and the lesser the time to calculate, the faster the programs run. This is just one example of how a better optimization of the calculations can improve the computer's performance. There are many procedures that can be done either in a dumb or in a smart way, and the research of better methods is one of the first techniques to optimize the computer's processing power. For those who play video games, better calculation means same GPU, better graphics. Now I ask you to pay attention on another characteristic of this theorem, which is, it covers an infinity of different cases. In fact, there are endless multiples of 3. We couldn't verify the fact for each number because we'd need endless time. So proving a theorem that covers it all in one shot is the only way we have to solve the problem. You'll see, we will study a lot of theorems that seem useless, but they are useful a lot to solve problems of real life, to do things we do every day and we don't notice. The last thing we need to talk about is definitions. Definitions are just the accurate description of what we mean with one word or a set of words. In mathematics, we need definitions very much because they outline precisely the properties of the objects we have to treat. Before explaining why this is important, why definitions are important, I will make another example of what a definition could sound like. A bottle, it's a lengthened container sealed with a cap and used to transport liquids. You can easily recognize these characteristics in the first container in the video. Instead, the second one is a jug. And why the second is not a bottle? Because it's not lengthened. That is, one of the characteristics listed in the definition is not respected. Please notice we are using words in definitions. And words' meanings need themselves a definition. So we should define what container means, what cap means, what liquid means, and so on. Guess what? You do that in mathematics because you need it. When it comes to use properties of an object in a proof, there must be no blurred lines. The definitions have to list perfectly what are the properties so you can use them to achieve what you are trying to achieve. As with the axioms and theorems, here we're having again a loop problem. That's because you have to define the words you're using in a definition, and you use words to define the words you're using, so that goes on forever. So again, we need a primordial concept that works like axiom worked for the theorems. The solution is taking for granted that everyone understands certain concepts by common sense. These concepts are called primitive concepts. The easiest example that came to my mind to make you understand this thing is about sets. In maths, we use sets all the time, but we never define them. Just for this time, if you want, you can go on Wikipedia, I authorize you, and you can read what they wrote there. They wrote that it's a primitive, intuitive concept left undefined because they presume the human experience of putting things in boxes since we were kids, and we had Christmas with parents and the aunt was pitching your cheeks. We should be familiar with that. Just to go further, you can see on the screen a set of houses and a set of people. No need to explain anything here. Definitions are the personification of the concept of abstraction. But what does abstraction mean? To abstract derives from abstraere in Latin, where abs means away from and traere means to take. So that's literally to take away. That's take away attention from the instance, from the reality here and now. This because we want to forget the first impression that an object gives us and, moving away from it, find out what makes that object recognizable. Guess what? I'll give you another example. The first example will involve cars. Let's take two Fiat Panda, a white one and a red one. Of course, they are not the same car physically, because one is red and the other is white, so one will be mine and the other will be of the Cesium man. By the way, it's also obvious they have a lot in common. That is, everything but the color. So if we compare the concept of red Fiat Panda and the concept of Fiat Panda, we see that they will be the same, except the fact that the concept of red Fiat Panda requires the Fiat Panda to be red. That's one more thing than the other concept. So the concept of red Fiat Panda is less abstract than the one of Fiat Panda because it gives us one extra concrete element, the color of the car. Now, if we take a Citroën near the two Fiat Pandas, we will still see some common traits, but also that the Citroën is very different from both the Pandas. That's what leads us to define the concept of car. The definition could approximately sound like private vehicle for people transportation with four wheels and white light on the front end and the red ones on the rear, etc. Now I will slow down a bit because I have to explain a delicate thing. Let's stick with our example. Car is more abstract than Fiat. That's more abstract than Fiat Panda. That's more abstract than red Fiat Panda. How do we verify this? If we take car, it is more abstract than Fiat because it's more general. That means that all the Fiats are cars, but not all the cars are Fiats. Cars can be Ford or Mercedes or something. If we move a step down, Fiat is more general than Fiat Panda because all the Pandas are Fiat, but there are many Fiats that aren't Pandas, and so on. If we want to abstract more for exercise, we can say that a terrestrial vehicle is more abstract than car, because a car is a terrestrial vehicle, always, but not all the terrestrial vehicles are cars. There are motorbikes, scooters, tanks, a sack full of other things. Can you hear the question coming, the one I always do? Can you hear? Why is this stuff important? Because if we prove something for an abstract concept, that fact will be true for all the less abstract concepts, sons of the more abstract one. Let's do another example of a theorem, a concrete one. We could say that a car parked on a flat ground can't be rolled over by the wind. If I now say Fiat Panda instead of car in the sentence is still true because Fiat Panda is a car. But if I say terrestrial vehicle instead of car, so no terrestrial vehicle can be rolled over by the wind, that's not true, because in the terrestrial vehicles there are motorbikes, and motorbikes can be rolled over by a strong wind. Just to make another example, let's create another theorem. If terrestrial vehicles run out of their energy source, they have to stop in a finite time. If we now say in the sentence, instead of terrestrial vehicle, vehicles with tires, or cars, or Fiat Panda, the sentence is still true. So abstraction permits to cover a bigger set of cases with one proof. Well, I think it's enough for this video. If you have any doubts, I'm here, just leave a comment. Sorry for my bad English, I'm trying to improve it. It's tough, but we will do it. And see you to the next video. Bye!